All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Maani Ghaffari, who is an assistant professor at the Department of Naval Architecture and Marine Engineering and the Department of Robotics at the University of Michigan Ann Arbor. And there he directs the Computational Autonomy and Robotics Lab, abbreviated as CURLY, which is a very nice acronym. So something about Maani. Maani received his PhD degree from the Center for Autonomous Systems at the University of Technology in Sydney, Australia. And his research interests lie in the theory and applications of robotics and autonomous systems. And as you have seen from the bio I shared with you, his work has received a number of awards, and he is active on many different aspects of these systems. And today's talk in particular will focus on computational symmetry and learning for robotics. This is clearly dear to the community of Autonomy Talks, and I'm very excited to hear more about it, and I let you the stage, Maani.
Thank you for the warm introduction, and it's a great pleasure to be here and sharing some of our work with you. The talk is about computational symmetry and learning for robotics, but you will hopefully see and relate it to lots of robotics problems ranging from perception and control. Now, a very quick motivation, you're probably all roboticists and you may expect this, but it will be impossible to build infrastructure and everything around us for robots in the future. We're just not capable of doing that. The future is uncertain. So much of what interests me is building autonomous robots or intelligent robots that can operate in highly unstructured and not known environments. Although that in some of the results are sometimes indoors, but this is the goal, which has a variety of applications. You may know, helping with population decline, need in labor. We'll all love to have a robot at home, obviously, to do our work. And helping with agriculture and aging population and so on. But it seems that we're very far from realizing that despite all the advances in AI and robotics, and the problem seems to be very difficult to realize. So the question is, what is missing and how to build these robots for the future? We can look at it from a variety of angles, and by no means I'm claiming that this is the only thing, but what we've been focusing on, and which matches our interest and background, is looking through the lens of computational symmetry. So we could convince ourselves that this problem is important as an umbrella problem. First of all, because it's a unifying framework. It brings in so much of mathematical physics, all the achievements we have in math and physics for understanding the universe, and achievement in by inspiration methods such as neuroscience, computational neuroscience, and biology for understanding animals and environments, and in engineering, in sort of a unified framework where we can use a lot of rich tools to study embodied intelligence realized as robots. Not specific to robotics, but we're motivated for sort of physical AI and platforms that act in the world eventually. So the computational approach, to break it down, why computational symmetry? Computational approach to intelligence seems to be indispensable because at this point, we cannot imagine AI without computation. NVIDIA becoming the most valuable company in the world, that's the proof of that, the entire progress is running on parallel processing, computational graph, and being able to run our algorithms using differentiable programming. And in a sense, we no longer seek analytical solutions unless these are small, fun problems to solve. We often aim for some form of optimization and numerical solutions in the context of optimization and programming. And the reason behind symmetry is really what is missing in a current AI systems, and that's the ability to generalize. So generalization is a big problem, and you can study it in a different context. For example, you might be interested in a particular problem and the domain might be limited, and as long as you can collect enough data and interpolate among the examples, that might be good enough. But the examples I showed in the beginning, but we might face a completely challenging and unknown and unstructured environment and dynamic and evolving environment. Then we need to be able to generalize. It is sort of believed that this ability is enabled in humans by means of abstraction and association. So generalization requires some sort of abstraction. That means I need to think beyond the specific things that I see and sense, and being able to understand them as a category, if you will. And that means I need to associate these categories and within abstraction that I can model and establish equivalence classes. So symmetry is really to enable equivalence classes. And that seems to be important for generalization capability, as I'll show, that's backed up by some results. Which it's a double-edged sword. You know, when I teach Lie groups to my students, they always complain that it's too abstract, which is my job to make them more accessible. And much of my effort has been to basically make these rich mathematical structures a common man's toolbox. That's part of my work. Still trying to do that. It's not easy. But on the other hand, when they say that, I am happy to hear it, because that's what we need. We need abstraction. So I'm sorry that they feel that way, but that's also the goal. So I cannot rectify these two feelings yet. So putting it all together, if you run a PCA, you know, and things are going on, I think computational symmetry is an important direction to look at different problems. It's an independent direction because you might solve and study a problem without looking into its symmetry structure. It's not necessary to look into it, and often we can solve it. For example, if learning and optimization embodies the entire, let's say, dynamical systems, estimation, control, optimization, machine learning literature, they're not necessarily looking into the symmetry structure, and yet they're able to do a lot with that. And building robotic systems, we've been very successful building hierarchical structures and control structures and artificial intelligence structures for robots and program them to be able to do it. But we need new principles, and that's very difficult to do. That's a direction that takes a lot of effort to come up with the principles of autonomy, in the sense that how would you integrate, how would you design the systems all together, and we can integrate them. And I think the progress is much slower in that direction. So much of the thing I'll talk about, it's in the XY plane. So I don't have any new principles for robotics per se today. So a recurring tool, and the more you learn, the recurring topic that shows up underneath of all of these topics, you know, in the related mathematical literature and physics and engineering, is Lie group. Because often we're dealing with some type of space, and often homogeneous space, and there's a symmetry group that models that space, and that's a Lie group. For example, rigid body motion, we're familiar with special Euclidean group, or a special linear group of dimension 3 is the homography group in vision. And typically, configuration spaces of robotic system can be modeled using Lie group, the famous book of Lynch and Park, for example, that is a common reference. It is built on Lie group, and it's a very nice resource. Or a state estimation book by Professor Tim Barfoot. Likewise, everything is studied within machinery of Lie groups. So this is very nice because for several reasons, Lie groups are, particularly if you focus on matrix Lie groups, we can really do algebra and matrix multiplication to handle some nonlinear objects. And it sort of reduces the burden of differential geometry to computation within a simpler framework. But also the existence of Lie algebra, it's a local linearization of the group at the identity that carries much of the group structure locally. And we can basically work with a vector field that captures a lot of the group structure. That's very appealing to do algebra and computation using these methods. So with all that story, so the first problem that It's very fundamental, and comes up in robotics as a state estimation. The robot needs to know where am I, how fast I'm going relative to a word frame. This is whether we talk about it or not, this is the capability we want in the robot. But these frames are inherently rigid body motion, so they operate on some sort of Lie group. So the first progress that I'm going to talk about is a library called Drift, the reckoning in field time. Drift is, as the name suggests, the reckoning is not a localization. It can track for a very long time using only proprioception. This was believed to be impossible for a long time. That means walking blind or moving blindly and being able to track for a very long time, and by long time I mean several miles in arbitrary situations. So what enabled this is a version of symmetry preserving filter became popularized under the name of invariant Kalman filtering. It's a very special filter. It's an error state Kalman filter that evolves on the Lie group. So it says that if your dynamics evolves on a matrix Lie group, and it satisfies a property that it calls group affine property, that property of F that you see here. We can plug in and check if the process model satisfies it. Then you will get an error, log linear error dynamics that is independent of error state. And as a consequence of that, given an initial error, we can recover the nonlinear error exactly at any time in the future. So that's very surprising for nonlinear systems, that we can recover the nonlinear error exactly at any time, which avoids the positive feedback loop and divergence in the common linearization. This is due to Baru and Bonabel and the previous literature on this topic. So the error definition, unlike traditional method that often decouples translation and rotation, we think about everything as a group, as a consistent matrix Lie group. Define the error used from right or left using matrix multiplication that corresponds to the group operation. Here, matrix multiplication. That error is invariant to left translation or right translation by another group operation. So it's invariant under group multiplication. So that means the error propagation does not depend on where we are in the space. It only, as we'll see, depends on how we move, in a sense. That's obviously reasonable because inertial frames of global coordinates are arbitrary. A typical animal does not have a sense of what word frame we choose or what generalized coordinates we might choose. So it ends up being something like a Kalman filter with a multiplicative correction. The tangible results that matters for engineers is that when we code it in the computer, in an ideal case, when there's no bias and noise, the Jacobians, when we linearize these error dynamics, are constant. So you get an observer on matrix Lie group that's important for robotics that acts very much like a linear Kalman filter. So we sort of use this in the lab a lot and implement it in a library. I'll show you videos of the results. You can see we have an Lego robots, full-size robots, Husky robot, indoor robot, and some simulation of marine robots. So the filter only uses IMU and kinematic data. And optionally, if we have multiple sources of gyroscope, we can improve the gyro data by linear filtering. This was interesting because we went to Pittsburgh in collaboration with Neo Systems and collected data on a full-size vehicle. It's an off-road vehicle. So at the end of this path, you can see that the filter is getting almost RTK GPS style accuracy using only a single IMU and shaft encoder, I think just from the front wheel. This was over, 1 mile. And this is really, simple, fetch is going into a kitchen, a super small area. And it's feature-based SLAM and state-of-the-art. It's a very remarkable framework. Of course, SLAM is solved unless when it doesn't work. It works, but you see the scale is off and not as accurate as you hope if you would want to build a map. But using IMU and encoder, we get better accuracy, although it's not a SLAM, not comparable. This one, we drive the Husky for 2 kilometers on campus for 55 minutes. And it's still, the accuracy is very close to GPS style, in the sense that the robot is not lost. It's within a nearby that you can easily close a loop if you run a loop closure detection. It's very interesting. So the limit is not the filter. The limit is battery of the robot and the time we can spend to collect data. And you can put it on a variety of platforms, underwater drone or air drone. And as long as you have a body velocity measurement, you could run this filter off the shelf. But of course, there's no actual sensor to give you body velocity measurement, except for wheeled or legged platforms that are in contact, or marine robots when you have DVL, Doppler velocity log. For drone, for example, you might need to use kinematics of the rotors. So a good problem we're interested to solve is, can we use IMU to get accurate body velocity? Now, the dual problem is very interesting because we use MPC a lot at this point in robotics as a tracking controller, and that's really one of the best tools we have from control theory to do online tracking using optimization. However, often the tracking controller that we have are nonlinear MPC. So by looking at the symmetry structure, we are going to formulate a algebraic, basically a formulation of the problem. So if you define the reconstruction equation, which is a kinematic equation that comes by default with any matrix Lie group, that tells you how the system, let's say a pose of the system, C3 matrix is evolving, and you have the true kinematic equation. You can define the error, and the aerodynamics, as you will see, when you do the calculations, it ends up being independent of the actual state variable x. It has this velocity error, which is the error in twist, and this adjoint map, which is a similarity change of basis, basically to map these velocities from different frame of reference to each other. It only depends on the error. So it depends on the error, but it does not depend on the state. Likewise, the beauty of the algebraic formulation is that instead of using generalized coordinates, if we work with exponential coordinates in the Lie algebra, we can get Euler-Poincare equation. These are symmetry reduction of what you may know as Euler-Lagrange equations. What happens, we get the twist dynamics. It does not depend on x, so it is only in the Lie algebra. This is for SO3, this is Euler equations, I omega dot equals omega cross I omega plus torque. This is for SE3 is a 6-dimensional equation of motion. But it is nonlinear because of this Coriolis term, cross term. So if we linearize it, the aerodynamics in the Lie algebra, you see, does not depend on the configuration state. We can also linearize dynamics to basically get a linear constraint. And what you could do, you could just do a simple discretization using Euler and integration and put an MPC together. And the difference is that this MPC is convex, although it's solving a rigid body tracking controller for 6 degrees of freedom, 3 for rotation and 3 for translation, it is convex. And we can solve it using off-the-shelf QP solvers, for example. One particularly interesting example is that we can apply we applied it to Lego robots, but another example is that we can apply it to marine vehicles. So marine vehicles are very interesting because you also have this domain that basically puts external loads that are very different from air because the density of water is much higher, so you get this hydrodynamics loads and waves current load on the vehicle. And the frequency of these loads are much lower than the high frequency controller that we run. So it's not easy to sync and compensate these loads by just acting faster. So this is the basically simulation that we run this MPC and compare it using nonlinear MPC. The performance is similar or slightly worse because this is not a physics-based simulation, unfortunately. It's a math-based simulation, so the nonlinear MPC uses a more complete model. But a good thing is that it's 10 times faster, which is very important for MPC because we can increase the horizon when we run this MPC in real time. So that's the lesson we learned. Plus, it's QP, and as you may know, the recursive feasibility is not very easy to show in typical nonlinear MPC, and being able to have a convex MPC that makes it at least to have a feasible. If the solution set basically is not empty, we're sure that we have a solution at any time. So that's the two first works that I talked about, they were based on invariance idea, but there are extensions based on equivariance, and those are also very interesting, but mathematically more involved. Those are more classical examples of computational symmetry. They don't necessarily have learning, which is why I separated as an independent direction. But we could have learning, which makes it more interesting. And recent work that we did that this is actually accepted for ICML now, we call it linear neurons. So the insight is that if you imagine MLP, every activation in a multi-layer perceptron is a scalar. And there was an extension of that to vector neuron when you think of it as a vector. A more general version of it, when I think about it, is when you think of each neuron itself as a Lie group or as a Lie algebra. This is very different to think about the entire network to model a Lie group like group convolution that we talk about. I am talking about every single neuron itself is modeling a group or category. This category level formulation allows for building a very complex models that can handle a variety of problems, including local symmetries. We have not looked into it right now. Our results are for global symmetries, but it's interesting to model local symmetries that belong to different categories and groups and their connection using different ways, for example, horizontally or vertically connecting them. That's the idea, but we call this linearon. And the way really we can realize this is because to build a equivariant network, you would need an invariant function. But every Lie group, up to semi-simple Lie algebras, these groups come with a conjugation invariant form. It's called trace form, and this is really the killing form. So what happens is that we can model functions in the Lie algebra that are equivariant to the conjugation. Why conjugation? Because the group action on group representation on any vector space can take different forms, but the group representation on its own Lie algebra, it's usually captured through conjugation or adjoint map. In simple terms, this means that everything in the Lie algebra is similar up to conjugation. So we establish an equivalence class among every vector or every function in the Lie algebra up to conjugation class. This is extremely powerful because we know how to abstract and associate similarities based on conjugation classes. In terms of very, very basic, matrix multiplication, this means change of reference, change of basis will not change the phenomena. The frame of reference, when we observe something, a velocity, for example, will not affect the result. So there are some technicalities, but in the very high level, we can build linear layer, ReLU layer using this invariant form. Interestingly, we can have a nonlinear layer using Lie bracket. This is very similar to residual network, but instead of Euler integration, now we have Lie derivative. So what comes in gets out with a differential using Lie derivative, which is the Lie bracket. And it's very interesting to have this sort of a first order integration layer in the network. And it is a nonlinearity because Lie bracket is nonlinear, but it is conjugation equivariant. Building invariant layer is very easy. We just stack these killing forms to get invariant layer. So we can have equivariant and invariant. Equivariance allows us to know how things covary. When we transfer the input, the output covary with the same basically in a predictable way. So we can have the knowledge of transformation in the feature space. And invariance, of course, can help with a lot of tasks for detection and classification. A few interesting examples, depending on your background, you might find them abstract or very interesting. Baker-Campbell-Hausdorff formula. So this formula is important because the product of two exponential for two matrices X and Y that do not commute, because matrix multiplication is not commutative, it's just exponential of some other number Z, and Z is not X plus Y. In general, what it is, it's an infinite series known as BCH that you can write it down completely based on infinite addition of nested Lie brackets. The importance of BCH is that means there is an operation called BCH in the Lie algebra, which is the linearization of the group in the at the identity tangent space, that completely captures the group operation on the group itself, which is a matrix multiplication, which we could basically study the group structure in the Lie algebra directly. This is the importance of BCH. And in robotics, it's used a lot for linearization, for example, in SLAM, for graph SLAM, state estimation work, and generally for, we can think of it as a Lie algebraic version of Taylor expansion, in a sense. So this series is equivariant, and we model with MLP, vector neurons, and Lie neurons. You can see that it's almost unaffected. The results are the same on test set and training set and test set. We tested when we rotated, we changed the frame of reference. If they're similar up to conjugation class, because this network Lie neurons is correct by construction, it should not be affected by that, and that's what we observe. Obviously, an interesting problem is that can we go back to that Euler-Poincare equation and learn the equation of motion? This is for a rotating body, a satellite. We model the inertia after the International Space Station. So it's a freely rotating body. There's no external forces. And we want to learn the equation of motion. You might be familiar with the neural ODE framework. It's a very interesting framework that we grab a neural network like MLP and learn a vector field and use an off-the-shelf ODE and backpropagate using a joint equation to train it. So the neural network ends up being our vector field, and later we integrate it. Well, ends up being the dynamics. Very interesting framework that adds continuous depth to the network. We replace any neural network that is typically MLP with lean neurons because we know the Euler's equation for a rotating body is equivariant. It is equivariant because inertia undergoes a conjugation if you change the reference frame. It's easy to show the equivariance. And on top of that, we can also learn the inertia as in here is implicit, but I think it's possible probably to make it explicit as well if there's an interest in that. So given an initial condition, linear neuron is supposed to learn the vector field omega dot, and ODE solver will give us the prediction of the trajectory. So what happens is that when we learn this, as you see in the phase space, it almost matches the ground truth, which is very promising. Now, when we train it on multiple trajectories and test it on unseen data with the change of frame, that means we apply conjugation to change the frame of reference, the performance of linear neuron is unaffected, which is expected. It is correct by construction in the sense that you would call contrabarrier functions correct by construction. It just does not have any other way to go wrong because it understands all conjugacy classes and their association. So the performance is exactly the same. So the very interesting part is that on a single trajectory, we can train and then test by applying conjugation to that trajectory to make it a test set. And the performance is still the same. And although it's a little lower because it's still good to have several examples, the performance is actually good. You know, the first 5 seconds the error is very low. And as you move forward in time, obviously the error will increase because we're just integrating. And this is without any fancy integration. We could, you know, to properly integrate a dynamical system, we could also obviously look into variational integrator, preserving energy, and so on. We're not doing any of that yet. Another sort of artificial, you know, or simulated example is that we want to have a very complicated function, say on the algebra of a special linear group, homography group, or volume preserving linear maps. If you define it, we can fit this function easily with errors that are close to numerical zeros. This is not possible with multi-layer perceptron. Although if you do argumentation with multi-layer perceptron, it does solve the problem much better. But the goal is to generalize, not that if the network has seen everything, then they can solve everything. That's I think that's a separate story, and there's a merit to that idea for a lot of applications. Another example is a platonic solid. We want to change the perspective. This is a homography estimation task. We want to change the perspective and then classify if the object is tetrahedron, octahedron, or icosahedron. This is object classification, a simple object classification task. And this is when we apply the rotation to change the perspective, the accuracy is sort of unaffected, which is also very promising. And MLP, you see the drop in performance. So this shows that a very promising direction that we've been occupied with, and it's not non-trivial, is to build image processing methods that are equivariant to a special linear group of dimension 3. This seems to be a very promising direction. Okay, so Another framework that this is sort of older framework of machine learning, kernel methods in RKHS, reproducing kernel Hilbert space. That is also equivariant. It's often not thought of it as in that way. Let's look into the point cloud registration problem. A typical problem ICP, you have point cloud red and you have point cloud blue, which is very common in robotics. You get it from RGBD camera or LiDAR. You want to find a rigid body transformation that makes that aligns these two point cloud that allows us to solve tracking, localization, and mapping problem. However, we do not know the association of these points. These points are discrete sensing of the environment. One idea is that lift the point cloud entirely into a function space, in this case, RKHS. That's an inner product space. It comes with a free metric that captures cross-correlation of these two functions. So the point clouds are seen as a whole, as a function. So we do not do point-wise association. We just maximize the cross-correlation of these two functions. Then the transformation will act on that function, as we'll see. So without getting into all the technical details, that by representer theorem, we know that every function can be represented as a weighted sum of some positive definite kernel, for example, a Gaussian kernel, with some labels. So we're gonna, and we don't need to normalize it in this case because we don't query. So, and we define some labels, but what it was sort of overlooked is that these labels, they do not need to be scalars. We can actually define a hierarchical semantic, hierarchical tensor space that can combine many type of labels, form of, say, vectors or matrices. For example, we can pick color and the semantic categories. You could get object category, and then all of these are labels. And then the kernel sort of is a geometric part that attached to this label. So the kernel captures the spatial correlation. These labels capture semantic information or correlation. And then what happens is that this is from linear group representation theorem, is that the transformation that acts on the function can act inversely, will act on the input. This is to preserve the group structure. So we don't actually need to look into the operator that will transform that function. We can directly transform the input point clouds, and this is very nice from the group theory. So we have a free inner product that captures cross correlations of two functions. The functions naturally interpolate among points. They see the whole point cloud as one, and then we align them to track. This was, as you saw in the video, very successful to have a joint model that captures semantic and geometry together. We don't want multiple, objectives and trade-offs. This is very integrated in that sense. Now the double sum, because this is an inner product of two functions with all the points as bases, it's a double sum in reality. It looks a little expensive, but it's actually sparse because the kernel bandwidth is always limited. So it's often the case is not everything with everything is associated, but you can think about it as a soft association. So every point is associated with a bunch of points. In addition, if we define the inner product on labels to also be another kernel, the dot product here, we can talk about similarities, association in the semantic space and association in the kernel space. So the things you could do with this is, if it's just frame to frame, it gives you a very superior front end for tracking. We have a CUDA implementation of it. It works remarkably well on highway, for example, when you're tracking at high speed, when the algorithm needs to interpolate a lot between points that we leave behind, and deals with sparse patterns and feature scarce environments very well. A multi-view extension of that is also possible. You could have a multi-frame formulation, and that gets closer to SLAM or some type of bundle adjustment, although not in the sense of classical bundle adjustment. You can do, these forest environments from tartan air, for example, is very complicated. These trees with little leaves are not very easy to associate. So this framework can handle tracking and function space very well. But also when we combine it with post-graph optimization, we get very robust LiDAR-based bundle adjustment. At this point, this bundle adjustment is not real time, it's offline, but still there are a lot of applications that we are interested in building a consistent map offline and reuse it. So another thing that I'm not pointing it out here, this method, the inner product in the RKHS space actually enables global initialization of the rotation in analogous to branch and bound. Because in a branch and bound, you have to do some search and define some upper bound, which is a slow process, and the natural metric is not clear. But in this case, you have a natural metric, and if you discretize the rotation group and do discrete search over which rotation is the maximizer of the cross correlation, that is your global solution, which is coarse, and then you can zoom in and do fine registration. You can see with the Maani example, for example, we can do global bundle adjustment very successfully. Now, this framework is important to know that it is equivariant, so that helps a lot with solving association without being affected necessarily by change of reference frame. It gives us a consistent cross correlation from different points of view. And a good thing about it is that it doesn't fail. Usually, even if it doesn't give you the best performance, it doesn't fail. So you can always rely on it to interpolate and track. But more interestingly, we can also bring that into equivariant deep learning, because now we can get the best of both. So grab an equivariant encoder, such as Lie neurons or vector neuron, and treat those equivariant features now as your new points. For example, in this case, we get the original 3D points, and the rotation features are coming from SO3 equivariant encoder, which gives you a tensor because you have the scriptors as well. And then the action of the group, in this case SE3, translation and rotation, is well defined in this equivariant latent space. We exactly know how these features translate and rotate as the input rotates and translates. Which means, again, we grab these features, we form a sort of a numerical learning-based version of RKHS by building the gram matrix that creates, by construction, it creates a positive definite kernel. And if you sum over all entries of this gram matrix, and it's not necessarily a square, but it looks like gram matrix, n by m, the sum is exactly the same inner product we had in RKHS, which gives us a metric to do unsupervised learning for registration. And it's very easy to backpropagate because the system is equivariant. Every time we update the pose with the delta, we just apply the new transformation to the feature space, because the feature space is not some obscure hidden layer. It's equivariant, and we know how to act on it. I think this is a very powerful idea, and as a result, we can do registration directly in the feature space. This connects classical works finally to geometric learning and deep neural networks. And we can get the initial proof of concept network is not necessarily very fast, but it's possible probably to optimize it. But it can perform it can outperform classical method and learning-based method, because often in the literature you see that they ignore the classical methods and compare with the learning-based method, or they ignore the learning-based method. But now we can just put them all in one category and compare. Okay, so I'm going to stop with this slide just to share some thoughts. It's been very promising and, in a sense, profitable to exploit symmetry and computational symmetry in particular in a variety of problems that are fundamental and we care about in robotics and AI. And so in a sense, asymmetry is inherent to the in the theory, but not in the phenomenon, not acceptable. It's better to formulate the problem correctly if that structure exists. And generalization is a promise of these methods by ability to abstract and associate by establishing equivalence classes. And my final thought is that, somewhat not related to everything I talked, but I think the new principle and theory we want is really memory optimal control. And this covers a lot of effort that you see it's going on, because by optimal control, I mean in the broad sense of variational problem that covers a lot of machine learning formulation as well. Memory will enable these systems to leverage data and being able to use that. But how to formulate it and how to solve this problem in an integrated way, the way we could talk about optimal control, it's not clear. And I think it's going to be very interesting as we discover more about this. So that's it for today. And I will stop here to see if there's any questions.
Thank you very much, Maani, for the great talk. I don't know, I cannot react anymore, but Zoom has this automatic reaction recognition. I don't know. Anyways, let's open the stage for questions. You can either type in the chat or directly raise your hand and ask. Maybe I can go first. So I mean, all of these 4 points are obviously very interesting, and I understand how they relate to your talk. What I'm really interested in is the points 2 and 3, which especially point 3, when you say that computational models are explainable. Can you, I think here you had to go fast because it was the end of the presentation, but could you elaborate a bit more on that point, on the explainability point? What are your thoughts there?
So this explainability comes from relationship of the representation layer and the input, because if I know how, assuming the representation is some finite dimensional vector space in practice, it cannot be infinite. And if I know, if I tweak the input to the network, exactly how the representation will co-vary, I am in charge, I'm in control, right? So it is no longer a black box. I know exactly how I am changing this, how I'm controlling this. Now, what's the nature of these weights and representation, what's modeling, I think that's sort of gets abstracted because it does not matter. It's problem to problem. It will change, the numbers will be different, but I can control over this. Now, in the sense of, this is not proven in some direction that I'm interested in. So probably we could just study all the classical, Lyapunov stability, for example, control. That's one of the things I want to prove, is that we could directly probably prove it in the equivariant latent layer. It just sounds so obvious to do it. That get rid of so many complexity of dealing with black box representations. So in a sense, it is nonlinear, but you're in charge of how it's changing. So that makes it explainable. Seems to be a good starting point.
Okay, yeah. So the idea is also, if I understand correctly, to then take classic tools for stability analysis, or you name it, to actually prove guarantees for these systems that are a bit, let's say, usually hard to characterize.
Right, because if say I want to, there's another thing that I think there are ideas, I tell people in the lab, we're only a few people, so it takes forever to do all of them. So let's say you want to design control barrier function directly in this representation.
Yeah.
It's totally possible. And you might have some assumptions, about the space and what's going on, about continuity. So often those assumptions that you see in literature are not necessarily assumptions you can verify or satisfy in practice. There are very, few occasions that you might be able to do it. So now that you have this sort of correct by construction representation that is rooted in math, you can actually enforce some of those assumptions by construction. So I think that makes it very attractive to me and explainable. It opens up the whole network. Now I'm working inside and I know what I'm doing.
Yeah. That's a very interesting take. Thank you. So any other question for Maani?
Yeah, I have a question. Hi,
Oh,
how are you
Christian,
doing?
go ahead.
Hi.
Nice talking to you guys. It was very interesting presentation, Maani. I have a question regarding autonomy. Can you elaborate a little bit more about what has been, done in this particular field for autonomy? I work with autonomy with very basic, digital twins and very basic, like decision-making algorithms, but this may be promising for, I don't know, maybe some more elaborate or elegant way of achieving certain aspects of autonomy. Thank you.
Thank you. Thanks for joining the talk and thanks for the great question. So that's a very good question because so autonomy talk, I'm giving you the pieces, but I'm not giving you the autonomous system. And that's because it's difficult. So I think that maybe the closest flavor of autonomy was this tracking controller, which is the really, really the lowest, level of that autonomy system. But it's not from our work, but it's not surprising that you can also build reinforcement learning methods that are equivariant. That's not a problem. The state, very much just like optimal control, you define, the Lie group structure and equivariance. But it's important the action space that also needs to have its own equivariance. Then what you would want to have is that to get a policy that is also coming out of maybe equivariant network. There are different flavors of it. I think in the most principled way, you could start making MDP, Markov decision processes, equivariant, and then look at equivariance with respect to action and state. And that's been done. There's some literature on it. I think those are very promising. I just haven't worked on it. But then you could imagine you could build a robot to steer. And that robot, now the policy, it will be explainable and efficient because what we learn from demonstrations, for example, right, is not affected that in what frame of reference I collected the demonstration. I just need a few examples to show the robot how to operate. And that will be sort of regardless of, what frame of reference I'm moving the robot, which is very powerful, it will generalize. And the reason I'm saying this, because in the learning dynamics example, from a single trajectory, we could learn a model. It wasn't the best model, but it was good enough for 5 seconds. So that means that, for example, you want to model drones dynamics, right? You collect data from many cameras, motion captures, put all of them in a data set. It means that you don't need that. You just need one camera. That's enough because, all the cameras in the room, by conjugation, by similarity transformation, are the same, right? But in the sense of data augmentation, of course, it's useful. So I hope that answered maybe some. I think
yeah.
Deep RL and bringing that and connecting it to the framework. Yeah. But I imagine we would want that deep RL and still we want this MPC to track that as a ref. RL gives us the reference and deep down we have this MPC track.
Yeah, thank you. Thank you so much.
All right. Thank you, Christian, for the question. Any other question? So in case not, I think, Maani, you gave your email somewhere in your final slide or your initial slide, in case people want to reach out.
No. Let me go back to the.
Okay, maybe it was in
Well,
the
search
beginning.
my name. I think it's very difficult for me to hide at this point. Working
Yes,
at
also
Michigan gives me a good visibility.
that's great, exactly. And also Curly is a nice catchy name that people will remember, I think. Thank you again, Maani, for the great talk. I will
Thank
reach
you.
out with the video once it's edited, but it's been great to have you here. And thank you everyone for joining, and see you all for the next Autonomy Talk.
Thank you.
Thank
Great
you.
talk. Take care, guys. Bye.
It's a pleasure.